Questions about anything from last time? Or about anything? I just finished grading the papers, and I'll release the scores later today in Brightspace, and Wednesday I'll return the papers and go over the exam. Looks like it turned out pretty well. So that's the plan. Questions? So it's an exciting lecture today, one I always really get a bang out of. I learned this from my thesis advisor, Norberto Kurtzman, who taught a course on it and got me real fired up about it. In fact, that's why I chose him, this course on Fourier analysis. Made me think I'll do anything that guy does for research. And we used a book by Dim and McKean that was a wonderful book. And I think Stein must have known about it because he takes kind of the same approach and does this in Chapter 4. So we need to start reading Chapter 4. Start reading Chapter 4, which does the isoperimetric inequality and the Weil equidistribution theorem, which I'm going to talk about. That's also a surprisingly easy thing when you look at it the right way. Let's see. So the key ingredients of this proof, it's going to allow me to use Fourier series. One is Green's theorem. I showed you. I talked about the inequality last time, so I won't repeat that. But it's pretty easy to come up with a isoperimetric inequality when you start thinking about a circle being the most efficient way to use area. And so if you have anything that's not a circle, that's a strict inequality. And sort of the more wiggly the boundary is, the worse that inequality is. And the Sierpinski snowflake shows that inequality can be way off by miles and miles. In fact, the Sierpinski snowflake, it's infinitely off. You get a thing with finite area and infinite perimeter, the Sierpinski snowflake. Oh, by the way, if you're going to talk about length, I guess the minimum you would assume is that the curve is rectifiable. That's kind of the most wild and crazy kind of curve that has what you can call a length. And of course, those more general cases are known. We're going to assume the curve's pretty smooth to use Fourier series properly. So anyway, the first ingredient is Green's theorem. I showed you this trick last time. We would write integral around the outside of p dx plus q dy. I want to get one-dimensional integrals to use Fourier series. So I can use the R version of Fourier series. And so the key is the left-hand side is going to be the kind of integral I want. I want this right-hand side of Green's theorem to spit out the area so I can estimate it somehow. And let's see, this side was dq dx minus dp dy dx dy. And I mentioned last time, let's try to make this side on the right here be 1. I'll settle for 2. So let's take q to be equal to x. Then dq dx would be 1. That'd be good. And let's take p to be equal to minus y. Then minus dp dy would also be 1. And so this thing would add up to 2. And so I would get here 2 times the area. So we get integral around the outside of p is minus y. So So it's going to be minus y dx plus x dy, q is x. That equals 2 times the area of the inside. I'll call that inside of the curve omega. Okay, so that's one thing I'm going to need. Another thing, let's see, there's a new formula involving stemming from Parseval's identity. So let's suppose I have an f of x given by a Fourier series. A_n cosine nx plus bn sine nx. And suppose I have another function, I'll call this one capital F, and this time I'll make the letters be capital. This is a Fourier series. So those coefficients are given by the Fourier coefficient formulas. Then Parseval's is going to give us, in a very simple way, Parseval's is going to imply that if I take 1 over pi and take the inner product of f of x with capital F of x, then I get 2 times a naught plus a sum as when n goes from 1 to infinity of an plus bn. So that's an interesting thing to look at. This is an L2 inner product right here. L2 minus pi to pi inner product. And this is a little L2 inner product. Little L2 inner product, where we're talking about little L2 is a square summable series. Little L2 is square summable. So that's a fascinating thing. This is another reason the vector space of L2 functions is kind of like it's like an Rn with n equal infinity, and the norm is the L2 norm, and those Fourier coefficients are like coordinates. That's a fantastic thing. L2 is the vector space. It's actually a norm vector space. It's actually a Hilbert space, which is a vector space with an inner product that's complete. L2 is the Hilbert space of square summable series. Anyway, that's just a remark. And let's see, the way we would prove this Parseval's thing, here's how, it's not hard. We'd write Parseval's for f plus f. And we'd write Parseval's for f minus f. And then we subtract those two. And the new formula we get when you subtract those, the little f squareds and the capital F squareds cancel out, and you get exactly that formula. So when you subtract, you get that new formula. That's all there is to that. So I'm not going to dwell on it. In fact, you have a homework problem where you are going to do that. It's not hard. You just do it. But we're actually going to use the complex version of that same thing. So the complex version, which you're also going to do in the homework, which is due after break, Thursday. The complex version is 1 over 2 pi, integral from minus pi to pi. And when you do an inner product in the complex case, you've got to have a conjugate in the second spot. And nice, there's no A's and B's, there's just C's. And the sum goes from minus infinity to plus infinity, little cn times capital Cn, conjugate. And that's the type of inner product you'd get when you have a complex version of L2. Okay. You're going to prove that in a homework problem. It's very similar to what you do in the real case. You just have to think a little bit harder. Okay, so those are the big facts. Let's see, there's going to be some steps to simplify the calculations. Which are reasonable. We'll rescale the axes. In fact, we'll just, if you think about it, you rescale by something like 2 pi over L. Rescale the axes so that whatever thing you have has perimeter 2 pi. That's going to make things easier. Then the isoperimetric inequality becomes, what is it? L over 2 pi. L is 2 pi, so L squared would be, then we want, that's isoperimetric inequality becomes A is less than or equal to pi. And if it's equal to pi, it's a circle. So that's the goal. We're going to show the area is less than or equal to pi. Another thing that's going to make our life easier, if we parametrize the boundary curve by arc length. Let's see, so we're going to parametrize it by z of, I'll make the z of t be a complex thing, or let's see. Sometimes I like to think about it as a complex number, sometimes I like to think about it in R2. But I guess right now I'll think about it in R2. So that's going to be a parametrization of the boundary curve, and we're going to parametrize it via arc length. And in fact, to make it feel like Fourier series, I'm going to make the parameter start at minus pi and go to plus pi, since it has length 2 pi. Why not? And also I'm going to assume that gamma is C2 smooth. So the x of t and y of t are going to be twice continuously differentiable. So I can use facts about Fourier series. So we're going to assume that a 2 pi period, so it's C2 smooth. And of course they're going to be 2 pi periodic C2 smooth, because they're going to hook up when they go around. When I extend it to R. Okay, we'll do notation like Stein prefers. He prefers the complex version of Fourier series. And in this case, you'll see why that's a good thing. So we have x of t of y of t. And remember, Stein's notation is a hat. X hat of n is the nth Fourier coefficient. So that'll be 1 over 2 pi, integral from minus pi to pi, of x of t, which is a real function, times the complex thing e to the minus int dt. And we'll also have a y hat of n, similarly. And here's something we showed earlier in the semester. So this is another key ingredient. If we take the derivative, x dot's going to be my derivative of the x function. If you take the Fourier coefficient of x dot, let's see. The way to think about that is if I write the Fourier series and differentiate it term by term. Let's see, I'm going to think in my head here so I can remember the formula. Let's see. X of t is the sum from minus infinity to infinity of Cn e to the int. Cn's are the x hat n's. X dot of t, let's see, this corresponds to, I guess I'll say equal, because it's a C2 smooth thing, so we actually get equal here. And this is, if you differentiate it term by term, you get in hat n e to the int. This is how to remember. Now that I've written that formula, now I can tell you the formula here is this Fourier coefficient of x dot is I times n times the Fourier coefficient of x. And this is how to remember the formula. Okay, that's how, that's going to be a key ingredient. And, of course, how to prove is the complex version of integration by parts. I think I've done this for you in the past. Complex version of integration by parts. You need to use the fact that they're 2 pi periodic, so there's no boundary terms. Integration by parts, let's see, when you do it, what do you get? You get integral from minus pi to pi of, let's see, I'm going to write it like this. That's integral from minus pi to pi of x of t, x dot of t. Let's see, I'm going to write it funny. I'm going to put my e to the minus int here, and then I'm going to put my x dot of t here instead. dt. This is going to be the dv. dv, and this other thing is going to be the u. And that's a complex integral, but when you write it out in terms of real and imaginary parts, you realize I can do integration by parts in both real and imaginary parts, and you get what you expect you're going to get, etc. So this would give you du would be minus in e to the int dt, and v would be equal to x of t, etc. And it works out just fine. Okay, now there's an important observation I need. When I get all the important observations written down, it's just going to pop right out. You won't believe it. So the important observation, since t is arc length, let's see, we have that means that ds dt is equal to 1. S is arc length and t, so the derivative of arc length with respect to arc length is going to be 1. So, in particular, ds, which you know the famous formula for, is x dot squared plus square root of x dot squared plus y dot squared dt. So this, we conclude, is equal to 1. X dot squared plus y dot squared is equal to 1. So we conclude, important, x dot squared, x dot of t of squared plus y dot t of squared is identically equal to 1. Those appear in Parsifal's identity. And therefore, let's see, the integral from minus pi to pi of x dot squared, that's something that shows up in Parsifal's square, y dot t squared dt, well, that's 1 going from minus pi to pi. That integral is 2 pi. But that's also equal to, by Parseval's, let's see, the Parseval's, the 2 pi I'd have to put on this side, since it usually is a 1 over 2 pi times that. And then I would have the sum of the Fourier coefficients. This is the complex version. So it goes from minus infinity to infinity. And this x prime's there, so that's going to be in x hat n modulus squared plus in y hat n modulus squared sum. Okay, so what do we get? We have written pi, which is, we want to get an inequality, something less than or equal to pi. So let's see, what we get when we play this game is that pi times, when I look at that, I need to do, I got a 2 pi there, so I'm going to divide by 2 and get pi times 1 is equal to pi times the sum from minus infinity to infinity of n squared times the modulus of these two things squared. Let's put that in a box. That pi is going to represent the area. Okay, now I'm about to do something. So recall, I'm ready to roll here. So recall, the area is a half times the integral along gamma of minus y dx plus x dy. And remember what this integral stands for. This is 1/2 integral from minus pi to pi, the parameter interval, and y is just minus y of t. And remember, dx stands for x dot of t dt. That's all that notation means. I'll put the dt over here. And x dy, and that would stand for x of t, dy is y dot of t dt. Okay. And now that improved Parseval's improved identity. Let's see, that's equal to 1/2 times 2 pi, and this is going to be the inner product in the complex sense, sum from minus infinity to infinity. So remember, it's going to be minus y hat of n, and now the Fourier coefficient for the x1, x dot, is I n x hat of n. And remember, this is a complex version, so there's got to be a bar there. And plus, the next one is at x hat of n, and the y prime is I n y hat of n conjugate. And then I put square bracket. Okay. I claim that soon it's just going to fall right into my lap. What do I want to see that I want to see that the area is less than or equal to pi. And it'd be a miracle if I can show that if it's strictly less, then it's a circle. But I will be able to show that. So I'm going to take, I'll use color coding here. I'll take pi minus a. And I'm going to write pi in the form, in a funny form. I've already written out once. So remember that thing, pi times the summation minus infinity to infinity of n squared times x hat of n squared modulus plus y hat of n squared. All right? That was because of the arc length business having derivative 1 and Parseval's. Okay, so I'm writing pi in kind of a weird, sneaky way. Perhaps it's fiendishly clever, but if you can prove the isoperimetric inequality, it's worth it. By the way, this is the beginning of the calculus of variations. So I'm trying to solve a max-min problem over all functions. That's a new wild and crazy thing called the calculus of variations, where functions are like points, and you're trying to get a max or a min over this whole space of functions. Okay, and remember my area, I just wrote it. So minus pi times summation minus infinity to infinity of, I'll pull the I n's out in front, and I get y hat n x hat n conjugate minus x hat n y hat n conjugate. Okay, the mind-blowing thing is that is a sum of squares. When I put that all together, that's going to be a sum of squares. and it's just going to be a routine playing games. So a mind-blowing thing. I want this. I'm going to have pi minus a. This mess, it's not a terrible mess, but it is going to be a sum of squares. And so it's going to be greater than or equal to 0. And of course, if that sum of squares is equal to 0, they're all 0. And that's going to be the case of a circle. So a fascinating thing is if they're all 0, implies the thing is a circle. So not only are we going to get the isoperimetric inequality, we're going to get that special clause that you only get equality if there's a circle. Okay? Well, let's see. You can read this carefully in Stein. I did some minor improvements from using Dim and McKean instead of Stein, but Stein does a nice job. So let's write. I'll write x hat of n is alpha n plus I beta n. And I'll write y hat of n, they're complex numbers. I'll write that little Roman an plus I Roman bn. Question? Let's see. So it's just algebra now. Algebra. Pi minus a. I look at that mess above, and that's pi times. When I write out those moduli, the modulus, I would get n squared times alpha n squared plus beta n squared. That's the modulus squared of the xn thing. And then the other one is an squared plus bn squared. Okay, that's the stuff that's the pi part. And now I take minus, let's see, I'm going to put the minus now. When you put that all together, I get minus 2n. There's going to be some cancellations. When I do those products there and write them all out, I won't bore you with the algebra, but stuff cancels. And what's left is minus beta n an minus alpha n bn. So, let's see, where's that? What am I looking at? That green thing, when I write those out and multiply them out, some inner terms cancel. And it greatly simplifies. All right? And the i's, that's actually a purely imaginary number inside the green bracket there. And so when multiplying about I it there is going to make it a real number. And that's exactly what happens here. So even though that thing looks like a complex number, all the imaginary parts cancel out. And I'm left with that as the real part. Okay, well, you'd have to be desperate. It's okay to be desperate when you're proving a math problem. You stare at that for a long time and you say, that's got to be a sum of squares somehow. And it is. Somebody, whoever did this the first time, should be famous, but I don't know who did this the first time. Because somebody proved the isoperimetric inequality without using Fourier series the first time. And the fact that you could do it with Fourier series was just an interesting side note, really. So let's see, how is this? You sit here for a few days and play around and think, how is this a sum of squares? It's n an plus bn squared plus n beta n minus an squared plus n squared minus 1 times an squared plus bn squared. Okay, let's see. N squared minus 1. Equals 0. Oh, let's see. I wanted. Yeah, that's n squared equals 0. Yeah, there's no 0th order term. I'm gonna change my. I don't like this thing right here with the n squared minus 1. So here's a convention. I'm going to choose my origin so that my choose origin so that the x hat 0, that's the average of x, is 0, and my y hat of 0, that's the average of y. Is that the center of mass? Probably not. No, it couldn't be. Anyway, I adjust my origin so that those averages are right smack at the origin. All right, the reason I'm doing that is I don't like that negative number right there. So So the reason is this looks like that's going to kill that one negative number. Kills one negative term. Otherwise, everything is going to be positive. And I can certainly do that. It doesn't change the area or the perimeter. Okay, so now if you think about, that's a sum of, all that's a sum of squares. So that n squared minus 1, that's for n equal plus or minus an integer, and not 0. So that's strictly positive. So we get n squared minus 1 is strictly, it's greater or equal to 0. Since the n equals 0, that's greater or equal to 0 if n is equal to plus or minus 1, plus or minus 2, etc. Okay. And now I've got a total sum. Everything in there is greater or equal to 0. So I get the isoperimetric inequality. So voila. Pi minus a is greater or equal to 0. So we get the isoperimetric inequality. Proved. But what if it's equal to 0? Then you look at that sum. What if the area equals pi? Then all those terms would have to be 0. And let's see what's the easiest thing to get. Yeah, each one of those terms would be 0. So, for example, the an and the bn's, little bn's, would have to be 0 because that last term, the there's a positive thing, n squared minus 1 is strictly positive. And so those things, if they add up to something strictly positive, if they're 0, then the an has to be 0 and the bn has to be 0. So the last term shows an equals 0, bn equals 0 for all the, for what's, n squared, yeah, let's see. The n equal 1 term, that would be 1 squared minus 1 in that last spot. So we see the last term shows that those are 0 for n equal plus or minus 2, plus or minus 3, etc. And maybe not 0. This is where the circle's going to come from. Maybe not 0. Maybe the A1 and B1 are not 0. Or the A plus or minus 1. Yeah. Maybe A plus or minus 1, B plus or minus 1 are not 0. Because that's the case, n squared minus 1 would be 0 in that case. All right, now we know the little ANs and the little BNs are 0. So those don't appear in those first two squares. And we conclude that alpha n's and BNs are 0. So next, the first two terms in that sum now show that the alpha n's and beta n's equal 0 over the same range when n equals plus or minus 2, plus or minus 3, etc. Basically what we get here is x of t is the complex C naught is 0 by my choice, and I would get a C minus 1 e to the minus it plus C1 e to the it. I just get the beginning of a Fourier series. All the other junk has to be 0. And I get the y of t equals some other, I'll call it curly c, plus curly c minus 1 e to the minus it plus curly c1 e to the it. And I want to see that that represents a circle. So I want to show this as a circle. This traces out a circle. And it's just playing games. So let's see. There's some little facts to know. So in doing this, there's little facts to play around with. Little facts that help. Let's see. Because these two things are real, x of t and y of t are real, x hat of minus n is equal to x hat of n conjugate. And y hat of minus n is equal to y hat of n conjugate. That's a no-brainer. The y is, just do it, x hat of minus n is 1 over 2 pi integral from minus pi to pi of x of t e to the plus int. And e to the plus int, oh, let's see, that'd be a minus n right there. E to the, I'm sorry, this is e to the, yeah, this is going to be it. Minus I to the minus nt. And that's equal to e to the int, which is equal to e to the minus int conjugate. Anyway, that's not a big deal. And when you play games with that stuff, and clean it up as much as you can, you get, in the case of equality, that x of t is 2 alpha 1 cosine t minus 2 beta 1 sine t, and y of t is 2 beta 1 cosine t plus 2 alpha 1 sine t. And one of your homework problems is to show that's a circle, and I give you a major hint that makes it a very easy thing to do. Okay, so this is just some analytic geometry that's pretty easy. And I'll give you a big hint about how to do that. Using complex numbers and e to the its makes it a very obvious thing. That's it. So I squeezed it in an hour. That's the kind of thing you have to sit down and look at it and see if you really believe it. But all the details are boiled down to some 3 or 4 basic facts about Fourier series. So I thought that was a fantastic thing to see. I would call it a highlight of the course. Any last-minute questions about anything? Okay, then. That's enough for today. I'll write a couple more details about the calculations here and post them. So I don't want to get bogged down with all the details, but I'll make sure all the details are there.
Included the step where you went from the you had the integral
Yeah.
with this, and then you equated that to this sum, this infinite sum. So are you just using Parsifals?
Yes, that's
go
the
from this
yeah,
here to
that's
here?
the Parsifals,
Okay.
the complex version.
I see. So this is like the this L2 norm is equal to.
That's an an L2 inner product of those two functions.
Oh,
And so
okay,
that's
okay.
going to be a sum.
Yeah, I see. Of the Fourier coefficients. Okay, got it. Oh, it's the Parsifals that you talked about earlier in the class. Where you
Yeah.
had the two functions.
Yeah.
Gotcha. Okay.